In this video, we're going to cover lesson number 2 inside of the second part of Unit 5 for college algebra. At the end of the last video, I asked you to read through and interpret these bullet points on your own. And at the start of this video, I'm going to provide my interpretation and my explanation for each. Now, first off, I want to point out that this numerator should look familiar to you, even if you don't quite recall what each of these terms mean. If we go way back to lesson 2 from the last part of this class, we noted that a polynomial is described in this exact same manner. And in the video for lesson 2 of part 1, I pointed out that we use this a sub n subscript from a n all the way down to a 0 because, well, there aren't enough letters in the alphabet to identify each coefficient, a through z. We could go beyond that in a complicated polynomial. Similarly, the exponents need to be whole numbers, and we identify the largest exponent and then decrease that exponent by 1 for every additional term. So the long and short of this phrase at the beginning here simply reminds us that a rational function is the quotient of two polynomials. And I'm going to write this as p of x over q of x, because p of x is what we traditionally write our polynomial notation as, and I'm using q of x down here so that I don't use p of x again. I don't want it to look like this is two of the same polynomials, so I'll use q of x to identify a different polynomial. Similarly, we use the coefficient with subscripts, the letter b instead of a, and that's our way of identifying a difference between the two. And instead of using n, we use the letter m for our degree and its subsequent exponents. During the last video, I think we pretty accurately determined or discovered that the vertical asymptotes of our rational function are the lines x equals a, where a is the 0 or a0 of the denominator. And I do want to add that the only time that we'll create an asymptote is when it's a 0 of the factored denominator, because if you recall, after the rational function is factored, we could have had factors that canceled out and disappeared. And if they disappeared, we called that a removable discontinuity. So the lines exist at a non-removable discontinuity. So we'll note that here. The lines x equals a create a non-removable discontinuity. And that's the location of the 0 in the factored denominator. As far as our horizontal asymptotes go, if we stick with this definition here, where n represents the degree of the numerator and m represents the degree of the denominator, degree of course being the largest exponent, then when the degree of the numerator is smaller than the degree of the denominator, then we always had a horizontal asymptote at the x-axis at y equals 0. When the degrees were the same, we saw this in a few examples in the last video, then the horizontal asymptote occurs at the quotient of our leading coefficients, a sub n divided by b sub m. And as far as an example goes with the problems that I led in the video, we did not encounter this third scenario where the degree of the numerator is greater than the degree of the denominator. In that case, there are no horizontal asymptotes. In the graph, the rational function never really levels off per se. Now, to these rules, I would like to add a third, and that says this, that there will be a slanted, or sometimes called an oblique, asymptote when the degree of the numerator is exactly 1 unit larger than the degree of the denominator. So if the degree of the numerator is equal to the degree of the denominator plus 1. And this asymptote will look like a linear function, y equals mx plus b. But in order to identify this, polynomial division is required. And so to supplement this video, I've got a few examples that I'd like to work through, and we'll see how many of these we can get through in this video. And the instructions state that we should identify the holes, the intercepts, both x and y, horizontal asymptotes. We should also note vertical asymptotes and the end behavior asymptote, especially if it's slanted. And with all of that analysis complete, we should be able to sketch the graph. So in doing so, one of the first things that I like to do is I like to factor the rational function. By factoring it, that gives us an opportunity to find our removable discontinuities. That'll allow us to find the holes, as well as vertical asymptotes. We should be able to determine our horizontal asymptote by simply looking at the original form. And the x and y intercepts, well, we can go either direction with that, either in factored form or original form, and we'll talk about that in just a second. Let's first factor. In the numerator, there's a GCF, and it happens to be 2x. In the denominator, there's also a GCF, and it happens to be x. With the GCFs out of the way, I'm left with two quadratic functions, so we should be able to factor them. Since these are standard, the factoring is pretty straightforward. In the numerator, I'm going to go with x minus 4 times x minus 1. And in the denominator, I'm going to go with x minus 4 times x plus 2. Minus 2. The product of negative 2 and negative 4 is positive 8, and the sum of negative 4 and negative 2 is negative 6. Similarly, the product of negative 4 and negative 1 made positive 4, and the sum of negative 4 and negative 1 made negative 5. So this is the factored form, and if we were to cancel out our common factors, what we're left with is 2 times x minus 1 and the denominator of x minus 2. Because this term and this x value will cancel. So with that preliminary work done, we've got an opportunity to answer some questions here. First off, our vertical asymptotes. Well, that's easy to identify because we now have zeros of the factored denominator. And so I know that at x equals 2, we're going to have a vertical asymptote. So I'm going to go ahead and sketch that on my graph. And as far as our horizontal asymptotes go, I'll note here that the numerator's degree is the same as the denominator. And so in that case, the horizontal asymptote is at y equals 2 over 1, or just y equals 2. And I'll note that on this graph as well. So I think that's going to take care of our horizontal asymptote and our vertical asymptote. So I should have updated my instructions here. So horizontal and vertical asymptotes. As far as our end behavior goes, we know that this graph is going to level off. There is no slanted asymptote in this example. But now it might be a good idea to find our intercepts. I think I'll find that next. Intercepts are pretty easy to find because the y-intercept occurs when x is equal to 0. So if I go back to this original formula, if I were to evaluate f of x at 0, well, I get an undefined result because 0, when substituted, especially in the denominator, creates a 0 in the denominator, which produces, again, an undefined result. But what's interesting is that if I substitute 0 in our factored form, we end up with 2 times 0 minus 1 over 0 minus 2. I don't get a 0 in the denominator. And this would simplify to negative 2 over 2, or in other words, 1. And so we're led to believe that there should be a point at 0, comma 1. When x is 0, y should be 1, but in the original function it was undefined. And what this tells me is that there is a hole right there. So there's a hole when x is 0 and y is 1. So at the coordinate 0, 1, I'm going to draw just a slight, tiny little hole. And by the way, we should have noticed that because this factor canceled when we were reducing our factored form of the rational function. So this guy produced a hole, and then this one's going to produce a hole. So while we're talking about it, let's go ahead and figure that out. What would happen if I substitute the number 4, which is a removable discontinuity? What happens if I substitute the number 4 into the factored form? Well, that becomes 6 over 2, or 3. And so we have another hole. When the x value is 4, the y value is 3. Here again, if I were to substitute 4 into this original function, by the time I evaluate this denominator, 4 cubed minus 6 times 4 squared plus 8 times 4, I would end up with a 0 in the denominator, which of course would produce an undefined result. So as far as graphing goes, if I run to 4 on the x-axis and 3 on the y-axis, that also is going to create a hole. So back to the problem that started this discussion, our y-intercept, well, there isn't any because technically the graph doesn't touch the y-axis. Our x-intercept, however, will occur when y is equal to 0, or in other words, when the result of this polynomial is equal to 0. And the only time that the polynomial will equal 0 is if the numerator, I'm sorry, I keep saying polynomial. The only time that the rational function will equal 0 is if the numerator equals 0. So I'm kind of running out of room here, so I'm going to jump off to the side. And I'll make a note that I'm looking for my x-intercept when the numerator equals 0. And that's essentially when 2x cubed minus 10x squared plus 8x equals 0. Well, again, we already noted that in factored form that this is 2x times x minus 4 times x minus 1 equals 0. And we also noted that when x is 0, that created a hole, so there's no x-intercept associated with that 0. Same thing here, that created a hole, so there's no x-intercept when that factor equals 0. So instead, what we're worried about is when does x minus 1 equal 0? And that occurs, of course, when x itself is equal to 1. So we end up with an x-intercept when x is equal to 1, the y-coordinate ends up being 0. So there's a coordinate, and this is a definite coordinate at 1, 0, this spot right here. So if I take a look back at my instructions again, it said to find the intercepts, which we've done. Identify the holes. We did that as a supplement or as an additional process to finding the intercepts. If this wasn't undefined, if our y-intercept wasn't undefined, well, we would move on to identifying the holes using this process, discussing when the denominator would equal 0 and substituting in this factored form. But we've got that. We should be aware that the end behavior, this graph is going to level off because of the horizontal asymptote. And now we'll try to sketch our graph. And I think we can do so from here. Sometimes there would be a need for additional sample points or data points to sketch the graph, but I think we've got enough information. Even though there are holes in this graph, we know that the branch or the leg of the graph does have to come through that hole. The graph is going to approach that hole but not quite touch at that point. And in this top right-hand corner, for example, if I had a branch of the graph that's kind of captured by this horizontal asymptote and then also again by this vertical asymptote, well then I know that it's got this branch in the top right-hand corner. Similarly, if I have a branch that has to go through the remaining 2 points, the hole and the actual x-intercept that we identified, well, it's going to be bounded or captured by these asymptotes as well, and the graph is going to tend to look like this. And if I want to reach for a calculator now to check my work, this would be a good time to do so. Really don't want you using a graphing calculator prior to this, but while you're working at home and checking your work, this would be a good use of one. And sure enough, here's the sketch, and I think it does a pretty good job of matching what we had expected. We have the horizontal asymptote at 2, a vertical asymptote also at 2. And what's interesting about Desmos is I think it can be used to identify or verify the holes that we find as well. Now, it doesn't look like there's a hole in the graph right now, but if I were to zoom in, and this has worked in the past, let's see if it works this time. If I zoom in on, say, the point 0.01, we should see something kind of interesting occur with the graph. Now, doing so on a regular computer would be kind of difficult to do, but since this is a touchscreen device that I'm writing on, I can pinch to zoom pretty easily, and, well, it looks like it's making a liar out of me here. I wonder if this has been fixed on the Desmos website. I used to be able to zoom in even closer than this. You can see how close we've zoomed in right now, and there actually used to be a bit of a squiggly mark here right at this position. And it was what I assumed is an error that's been fixed here, but it would appear as though the graph itself was breaking down right at this position. So maybe it doesn't work like that anymore, but Desmos used to be good for that. Now, of course, these holes are so infinitesimally small that it's not surprising that we don't see that point where it breaks down from this view, from our standard zoom. But if we were to zoom in indefinitely on a coordinate, then we would likely see that error. So just out of curiosity, I'm going to try this one. Just going to zoom in as much as I possibly can. No, there's a limitation there. It's not letting me zoom in any farther. So maybe that's a fix on Desmos' website. Well, the only other way that we can verify this is try to evaluate the function at 0, and we see the undefined result. And if we evaluate the function also at 4, we're going to be notified of an undefined result. Any other point that's extremely close to that will produce a calculated result. And if I just, go to evaluate the function at 3.9, it looks like the y value is almost 3. And if I jump just to the other side of 4.00001, well, that's almost 3 as well. So if the function result at an x value of 4 is almost 3 on either side, then I think it's safe to say that there is a hole right here at the coordinate 4, 3. So I think we've done a pretty decent job here. We've met the criteria, and we were able to sketch this graph. So let's try another example. As we did before, I think the first thing that we should do is factor. And I wouldn't, cancel all these terms out just yet. I'd just write this in factored form and then perform the analysis after that. So it looks like in the numerator we're dealing with a quadratic whose factors might be x minus 4 and x plus 3. In the denominator, we have a GCF of 3, and that's going to leave us with x minus 2. We don't have any removable discontinuities, so there aren't going to be any holes this time, so I might want to make a note there. No holes because of no removable discontinuities. But because of this 0 here, I know that there's going to be a vertical asymptote at x equals 2. Anytime that I'm left with a 0 in the denominator after it's been factored, I know that that's going to produce a vertical asymptote. As far as a horizontal asymptote goes, we want to look at our original format. And in this case, the numerator's degree is greater than the denominator's degree. So we should make note here that there is no horizontal asymptote. But also, since the numerator's degree is exactly 1 larger than the denominator, then there is going to be a slanted asymptote, sometimes called an oblique asymptote. And so we've got to perform polynomial long division in order to find that equation. I'm going to make a note here there's a slanted asymptote this time, and the work that we're going to do to determine that is going to be shown off to the side. And I would encourage you to do some more research and watch a couple other videos on polynomial long division so that you can make yourself better. But in this particular case, we're going to start with the numerator, x squared minus x minus 12, and that's to be divided by 3x minus 6. And the way I always perform my long division is like this. Off to the side, I'm thinking to myself, what would it take to multiply 3x, or what should I multiply by 3x to equal x squared? I tend to temporarily ignore the remaining components of the polynomial. I'm just going to do a rough estimate at this point. And sometimes I'll even write down the expression 3x times what equals x squared. And I know that if I multiplied 3 by 1/3, that's going to leave me with the coefficient of 1 that's desired here. And I know that x times x is going to give me x squared. So if I'm thinking backwards, I'm doing the opposite of division, and I'm thinking of multiplication, I know that 1/3 x times 3x will give me x squared. So there's my estimate, and this is similar to the long division algorithm if you've learned this in the past. If I had a number like 356 and I was told to divide it by 23, I don't guess how many times 23 goes into 356. Instead, what I might do is I might guess how many times does 20 go into 35. And in that case, I know that 20 goes into 35 one time. And so after I make my guess, I multiply this guess times our divisor here, and then we perform the long division process of subtracting, bringing down the remainder, and then repeating the process again. So that's essentially what we're doing with this long division. So this 1/3 x was my guess, and 1/3 times 3x is x squared, which is exactly what we want. And 1/3 times 6 is -2. X times, well, no other value here is going to be -2x. And so the product of 1/3 x and 3x minus 6 is x squared minus 2x. I have to subtract that product from the existing polynomial. X squared minus x squared is 0, which is what we want to see. We always want to see this guy disappear. Then -x take away a -2x. Well, that's the same as just adding 2x. And that leaves me with x. And I'll drop down this 12 and continue the process. I'm going to erase those to get them out of the way. And now I'm thinking to myself, 3x times what will equal x? Kind of like in this process here, I'd now be guessing how many times does 2 go into 12, or how many times does 23 go into 126. That would be my next guess that I place here. So in this example, I'm thinking to myself, 3x times what equals x, and that's pretty straightforward. 3x times 1/3 would equal x. So I'm going to guess 1/3 here. And now that I've made my guess, I'm going to multiply just to check my work. 1/3 times 3x does equal x. And 1/3 times -6 is -2. When I subtract these two, I'm left with 0 minus 10, because 12 take away -2. -12 take away -2 is like adding 2. And so technically what I have now is a remainder of 10, and I'm not really that interested in that. What I am interested in is the result that I get here. This linear equation represents our slanted asymptote. So the slanted asymptote was found by performing polynomial long division, and the slanted asymptote occurs at y equals 1/3 x plus 1/3. So if I were to sketch that, it's going to be kind of hard to do. I have to find 1/3 on the y-axis, which is right about here. And then I have to rise 1, so up 1 step brings me to the 1/3 mark of the unit above. and then to the right 3 units, and that would be right here. And then up 1 and over 3, up 1 and over 3, and so on. And I'd have to create a dotted line that goes through each of these points. Okay, so we now have some boundaries to work with. Let's see if we can find some data points to give us some more information. So I'm going to start with the y-intercept. Remember, the y-intercept occurs when x is equal to 0. And when x is equal to 0 in this case, let's go ahead and just make a note of it here. F of 0, this can be evaluated. That's going to be negative 12 divided by negative 6. I'm doing that because I know that each of these terms will turn to 0 pretty quickly and easily. So that ends up equaling positive 2. So we have an x-intercept at 0, 2. So this data point exists on the graph. And as far as our x-intercepts go, that occurs when y is equal to 0. And the only time we need to discover when y is equal to 0 is when our numerator is equal to 0. So when does x, I should have made note of that, x minus 4 times x plus 3 equals 0? Well, that occurs when x is equal to positive 4 or when x is equal to negative 3. So we now have x-intercepts at 4, 0, and negative 3, 0. So if I plot those, 4, 0, negative 3, 0, we've got some information to work with. And I think we're in pretty good shape. I bet we can sketch a graph with this information. So here again, this branch of the graph of this rational function has to be captured by this slanted asymptote and this vertical asymptote. And so if I were to connect these 2 points and then draw this line so that it gets bounded by those asymptotes, then it's going to tend to look like this. And for this one down here, I only had one data point, but that's sufficient for me to recognize that the graph is going to approach this asymptote from this direction and this one from here. If this data point had been, say, up here somewhere, well, then I might have drawn the graph to kind of curve down and approach the asymptote this way and then up this way, which is not unheard of, but that's not what our data told us here. With a single data point applied here, this leg or branch of the graph has to be captured by the asymptotes. And if I jump over to Desmos, we'll see the graph as we expected. Now on this one, I'm also going to graph the asymptote just to further prove my point here, 1/3 x. And that would not be sufficient because you'll notice that there is an intercept or intersection that occurs here. 1/3 x is not correct, but 1/3 x plus 1/3 on the other hand, now that does produce the asymptote where the blue line does tend towards. Lastly, I'll also point out that Desmos does graph points pretty clearly and easily as well. So we can use Desmos to check our coordinates here too. So we had a y-intercept at 0, 2. And that dot does appear to be on the graph. And the other 2 coordinates, negative 3, 0, 4, 0, our x-intercepts, they appear to fall on the graph as well. Now I don't want this video to continue any longer, but we do have a couple other examples that I'd like for you to try on your own, 2, 3, and 4. I'm sorry. Looks like there's 2 copies of this number 3. I don't know what happened there. 3, 3, and 4. So I'm not really sure what happened with this duplicate, so we can go ahead and skip that one. Why don't you try number 3 and 4, the second set of 3 and 4, these 2 examples, and if they differ on your handout, then make sure that you're doing these in the video. But try these on your own, and then you can come back in a moment to check your work. I'll have the solutions written up on the screen, and I'll try to zoom in so that you can see different parts of my work. It may be a little bit messy, but hopefully you'll be able to find where your work aligns with the work that I'm doing. And if we were to report this on a test, I'd have a more clear way of reporting our final answers. So anyway, try these two on your own and resume playback in a moment to check your work.